Good morning, Townview. Welcome back to Chemistry Online. So today we're going to be talking about acids and bases. And specifically today we're going to be talking about the pH scale. So at the top of your notes, you're going to write down acids and bases and then pH scale. All right, so what do we use the pH scale for? We use it to measure the strength of acids and bases. Now, most of you guys have seen pH for a long time. You see a lowercase p and a capital H. So the reason for that is because this is just the power of hydrogen scale. So the H stands for hydrogen, P stands for power. And each time you change 1 on the scale, you're increasing by a power of 10. So over here, we got the pH scale, which goes from 0 to 14. And then right here in the center, we got 7. And so let's say we had something with a pH of 6. So we know 6 is more acidic than 7. But how much more is it acidic than 7? So 6 is actually 10 times more acidic than 7. Now, what about 5? How much more acidic is 5 than 7? So this one's going to be 100 times more acidic than 7. So every time you move once on the scale, you're increasing by a factor of 10. This part right here we talked about last time, or 2 classes ago. So anything less than 7 is going to be considered an acid. 7 is going to be neutral. And anything greater than 7 will be considered a base. All right, let's move on. So this part right here just talks about the strength of acids and bases. We're not going to do that. All right, so when acids and bases combine, the pH changes. An acid with a pH of 2 is added to a base with a pH of 10. What is the resulting pH of this solution? So we're not going to be solving problems like this on the ACP. However, you will see something similar to this. For example, if you mix a strong acid with a weak base, what will the resulting pH be? You'll be solving questions like that. But I'm going to help you guys in solving stuff like this. So here's our 0. Here's our 14. Right in the center, we have our 7, which is neutral. An acid with a pH of 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So an acid with a pH of 2 is mixed with a base with a pH of 13, 12, 11, 10. So an acid with a pH of 2 is mixed with a base with a pH of 10. What's the pH of the resulting solution? So our solution is going to be somewhere in the middle. We're assuming that these are both strong acids or strong bases. It'll be more specific when you answer these types of questions. But assuming that they're the same thing, so strong acid with strong base or weak acid with weak base, your answer is always going to be somewhere in the middle. So here's our 2, here's our 10. Our answer is going to be here somewhere. So the resulting pH is going to be what? Acidic, basic, or neutral? What do y'all think? All right, it's going to be acidic. Good. So my suggestion for problems like this is draw them out sort of how I just did and see where your result will be. So let's take a look at the next one. So on the next one, you have a base with a pH of 12 mixed with a pH of 10. So here's our 12. Here's our 10. We mix these together. What's our resulting pH going to be? What is it? It's going to be 11. It's going to be right between those two. So it's going to also be basic. So here's how you're going to solve these types of problems. I'm going to show you more examples later on with regard to strength. But I just wanted to show you your answer is always going to be between those two numbers. All right, let's move on. Let's make sure we're not on our phones. I don't want anybody distracted. You know who you is. All right, so these are chemicals. What are indicators? So 2 classes ago, we talked about what was it that we talked about? We talked about litmus paper. And litmus paper is an example of an indicator, and it changes color based on the pH of whatever it is you're looking at. So indicators, all they do is they tell you the pH of something. Now over here we have a number of indicators. So you can see that there's a lot of indicators, and students very often ask, why do we have so many different indicators? So let's take a look at indigo carmine. So indigo carmine, anything between 0 and about 11.5, what color is that going to come out? It's going to come out blue. So it'll tell you if something is less than 12. But will it tell you any more information than that regarding these particular, regarding solutions that are between this area here? No, it's not going to do that. Where is it valuable? This particular one is really good if you have something and you know that it's got a pH between 11.5 and 14. Over here, it can get really precise. It's the only one that actually gets precise in this zone. So take a look at all these other ones. None of these other ones are very precise in that zone. So you use different indicators based on where you think your zone is going to be. That's why we have so many different indicators. In high school chemistry, the one we use the most is this one right here, thymol blue. As you can see, it gives us a very wide range, and it separates right here around the 7-8 mark. But anyway, that's what indicators are. They're really good at telling us how acidic or basic something is. This slide, you don't got to worry about it. We're going to keep on going. All right, next up, we have strong acids and strong bases. So everything I say right now about a strong acid also applies to a strong base. We discussed this last class, but today we're going to get a little bit more in depth. So a strong acid is one that fully dissociates when we put it in water. What does that mean? So it does separate, but what does it mean by fully dissociate? All right, you're not going to have any HCl on this side. So if you can see right here, we have a one-way arrow. Does this reaction go back and forth? No, this is a one-way reaction. After you put HCl and H2O, the HCl is going to separate and it's not going to reattach. So we have no HCl on this side. So strong acids, they fully dissociate 99% to 100%. So 100% dissociation. And that's it. That's what you want to know about strong acids. This also applies to strong bases. Over here with weak acids, you only get partial dissociation, which means about 10% dissociation. Which means over here, you can see that our reaction goes both ways. So a hydrogen is going to detach from the acetate, or sorry, from the acetic acid, and then it's going to reattach. And then another one detaches, and then another one attaches. So it just goes back and forth in this reaction. Let's keep going. With regard to base strength, so a strong base is going to do the same thing as a strong acid. You get full dissociation. And then a weak base is going to do the same as a weak acid, where you get partial dissociation, somewhere around 10%. Now let's talk about electrolytes. What are electrolytes? So salts are an example of an electrolyte, but what is an electrolyte? What does an electrolyte do? All right, they conduct electricity. Good. So what part of the electrolyte conducts electricity? What is it that actually conducts the electricity? What's floating around in the water? It starts with an I. All right, ions, good. So we just talked about strong acids and strong bases. So strong acids fully dissociate. So let's say that we have 1 mole of hydrochloric acid, which we know is a strong acid. And then we have 1 mole of hydrofluoric acid, which we know is a weak acid. How much dissociated hydrogens are we going to have in our solution? If we put 1 mole of HCl, how much hydrogen will we have dissociated? 1 mole, good. So we're going to have 1 mole of H plus. How much Cl minus? How much Cl minus? 1 mole of Cl minus. But then if we did the HF, how much hydrogen are we going to have? From 1 mole, how much are we going to have? How much hydrogen are we going to have? Point what? 0.1 mole of H plus. How much F minus? 0.1 mole of F minus. So how many more ions are in the HCl solution compared to the HF? How much more? All right, 10 times more. So there are 10 times more ions in the strong acid. So if there are 10 times more ions, which one do you think is going to conduct more electricity? The strong acid or the weak acid? All right, strong acid. So strong acids are going to go in this category. Strong acids are going to be what type of electrolyte? They're going to be a strong electrolyte. What about a strong base? What kind of electrolyte will that be? It's also a strong base. Strong bases go here. So strong acids, strong bases are going to be strong electrolytes, which means they conduct a lot of electricity. And the reason for it is because there's a lot of ions. All right, what about the weak acids and weak bases? What are they going to be? They're going to be weak electrolytes. So weak acids and weak bases are going to be weak electrolytes. You got to write it down in some form, yes. On the next slide, I'll give you complete sentences if you want to write those down, but this is what I'm trying to get y'all to understand. So strong acids and bases are going to be strong electrolytes because they have a lot of ions, a lot of free ions. And then the weak electrolytes, those are going to be the weak bases that have much fewer free ions. Now, what falls under the category of non-electrolytes? It starts with a C. All right, so covalent compounds. What's an example? What's an example of a covalent compound? CO2, good. CO2 is non-conductive. What about H2O? Does H2O conduct electricity? No, so that's going to be a non-electrolyte. Anything that's a covalent bond is going to fall under the category of non-electrolyte. Weak acids and bases are going to be weak electrolytes. Strong acids and bases, those are going to be strong electrolytes. All right, so let's move on to the next slide. So strong acids are what type of electrolyte? Strong acids are what? Okay, weak acids are what? Strong bases are what? Weak bases are what? All right, so these things you want to know. Let's move on. So strong acids, do they conduct electricity? Weak bases, do they conduct electricity? Are you sure? Yes, they do. They conduct less, but they do conduct. What about strong bases? Do they conduct? What about weak bases? All right, so all of these will conduct electricity. That's an important thing to keep in mind. All right, so let's see if you guys remember the properties. This is just everything. They all conduct electricity. All right, so let's see if you guys remember these. So taste bitter. Is that going to be an acid or a base? Taste bitter, like soap. Those are going to be bases. pH less than 7. Taste sour. Produce hydronium. What is hydronium? What is hydronium? It starts with an H. H what? What is hydronium? H3O plus, good. And what is H3O plus the same as? It's the same as H plus. So when you dissociate an acid and water, the hydrogens are free and they constantly attach to water molecules, forming this temporary bond of H3O plus. So keep that in mind. Hydronium, you're going to see it again. So hydronium ion is an H plus. So what produces hydronium? Acid or base? Acid, good. Feels slippery. Produce hydroxide. Has low hydronium ion concentration. That's going to be base. Dissociate in water. Both. Known as alkali. Which ones are alkali? Acid or base? Which one are alkali? pH greater than 7. Base, and then is neutral. That's going to be H2O. All right, y'all did good. Let's keep going. So now we're going to talk about calculating pH and pOH. So a lot of you guys have heard of pH. pOH is going to be new for you guys. So what does pH stand for? All right, power of hydrogen. So if you had to guess, what is pOH? What do we call OH? Power of hydroxide. Good. So anytime you have a pH for something, you also have a pOH for that same thing. We're going to be doing those calculations today. Make sure you're following along. All right, let's move. Okay, so the strength of an acid is based on the H3O plus, which we already said is the exact same as saying H plus. But these values are often very small numbers. To express small numbers conveniently, chemists will use the power scale, which is based on a log 10. Okay? You don't need to write this down. I'll tell you what you need to write. All right, so real quick, I want everybody to draw this exactly how you see it, and I want it to take up about a third of your page. We're going to do a little bit of defining once you're done drawing it. So let's go ahead and draw it real quick. Look. All right. Hold on. All right, so down here, that's a good question. So please, we're back on. So you have a total of 14 zeros, and the decimal comes after the first one. So it's 0.13 zeros and then a 1. All right, so what does this mean? So a pH of 0 is 10 to the power of 0. What is 10 to the power of 0? 10 to the power of 0 is 1. 1 is the same as saying 100%. So almost entirely H plus is in this solution. This solution is made up of almost entirely H plus. That's what a pH of 0 means. Over on this side, we have 10 to the power of minus 14. That number is a really small number. It's this right here. It's also this right here, 1.0 times 10 to the power of minus 14. Is that a big number or a small number? It's a very small number, which basically means there's hardly any hydrogen there, hardly any H plus. Now, here are the equations that you should have written down. If you didn't write them down, it's not a big deal. I'll have you write them on the next page. But I wanted you to have this pH scale just so you understand what these numbers actually associate with. So let's keep going. All right, so we talked about pH and POH. We said POH is the power of hydroxide. So here's what I want y'all to see. So over here at the top, here we have our hydrogen. It says 1 times 10 to the power of 0. What does that equal? That equals 1, basically 100% hydrogen. How much hydroxide do we have in this almost 100% hydrogen? Is this a lot, 10 to the power of minus 14? No, this is very little. We can call this 0.0000001. Like it's very, very little hydroxide in the solution. Now, if we come down here to the bottom, 14, where we know that our strongest bases are, it says 1.0 times 10 to the power of 0. What does this equal? This equals 1. Basically 100% hydroxide. So over here, we have almost 100% hydroxide. How much hydrogen do we have over here? Very little. So 0.00013 zeros until you finally get to a 1. So what I want y'all to see is as we increase the pH, so as our pH goes from 0 to 14, what's actually happening is our exponent is decreasing, which means there's a decrease in the amount of hydrogen concentration. And then over here on the pH scale, it's the opposite. So we start at negative 14, and our number is shrinking. So it goes from 14, 13 to 11, 10, all the way down to minus 1 and then 0. Our number is actually getting bigger as we move downward, and that's basically telling us that we're increasing the amount of hydroxide. Now, here's what I want y'all to notice. Here where it says neutral, how much hydrogen do we have? How much hydrogen do we have at the neutral mark? 10 to the power of what? Minus 7. How much hydroxide do we have at that same spot? What does that mean? What's going on at the neutral mark? We have the same number of hydrogen as we do hydroxide. When you have the same number of hydrogen as you do hydroxide, what are you dealing with? So hydroxide is OH minus, and hydrogen is H plus. If you have the same number of hydrogen and hydroxide, what do you have? You have water, H2O. So water is neutral because it's got the same number of hydrogen as it does hydroxide. That's what I wanted y'all to see from this particular chart. And as we increase the amount of hydrogen, we're decreasing the amount of hydroxide. As we increase the amount of hydroxide, we're decreasing the amount of hydrogen. Any questions on this? All right, let's move on. So you can convert concentrations of hydrogen and hydroxide in solution in terms of pH and pOH, and there are 3 equations that we're going to start with writing out. First equation is pH is equal to the negative log of H+. So go ahead and write this out. pH is equal to the negative log of H+. Now, this equation is not one you have to memorize. You could grab your periodic table. Right at the bottom of solutions, you're going to see the equation for pH. It says pH is equal to the negative log of your hydrogen concentration. They don't give you the one for pOH, but they assume that you can derive it. So pOH is equal to the negative log of what? Of your hydroxide. Now, one other thing you need to know is your pH and your pOH need to always equal what? They need to equal 14. So if you have a pH of 7, what is your pOH? And then that equals your 14. So these 3 formulas are what you're going to need to solve the first few problems that we're about to solve. All right, let's move on. All right, we're recording. All right, so let's go ahead and do some calculations. So it says, what is the pH of a solution where your H plus concentration is equal to 1.0 times 10 to the power of minus 9? So I'm going to start by writing out my formula. So pH is equal to what? What was the equation? Of what? Negative log of our H plus. So they're telling us what our H plus is, so we can go ahead and solve this. So everybody grab your calculator, press the on button, hit clear real quick, and then I want everybody to see your negative button. Your negative button is the one underneath the 3. Do not press minus or else it'll give you an error. Your log button is right next to the 7. So that's the one you're going to be using. So negative log, it opens up parentheses for you right away. And then you're going to plug in 1 times 10. And then you're going to press the caret, which is underneath the clear button. Caret negative 9. And then what do we get? We get 9. So our pH is equal to 9. You need to be plugging this into your calculator. No. So to calculate the pOH, what do we got to do? It's just going to be 14 minus 9, which equals what? So our pOH is equal to 5. Now, if the question said, is this an acid or a base? What is this? It is a base. What should we be looking at when we're trying to figure out if it's an acid or a base? You look at the pH. So if the pH is greater than 7, it's a base. Lower than 7 is going to be an acid. This one isn't a base. All right, let's move on. All right, let's go ahead and solve number 3. I'm going to give you guys 2 laps, and then we'll go over it. Okay, so let's go ahead and solve this one. So they're asking us for the pH, but they're giving us the OH. What can we use the OH to solve for? So we can use OH to solve for pOH. And then once we have the pOH, we can figure out the pH. So negative log of 1 times 10 to the power of minus 6. What did that give y'all? That gives y'all 6. And then 14 minus 6 is what? So we have a pH of 8. Is this an acid or a base? This is a base. Greater than 7 is a base. All right, go ahead and solve the next one. All right, let's go ahead and go over this one real quick. So for this one, they want the pH and they want the POH, and they give us the H plus. So what can we calculate first? We can calculate the pH, and what is the pH that you guys got from negative log of 3.4 times 10 to the minus 3? Is it 2.5? All right, so pH is equal to 2.5. So they give us two significant figures, which means our answer should have two significant figures. 2.5 is good. So if our pH is 2.5, what is our POH? 11.5. Is this an acid or a base? Are you sure? All right, this one's an acid. You should be looking at the pH. The pH tells you if it's an acid or a base. All right, go ahead and solve number 5. All right, let's go ahead and go over this one. So in this one, they give us hydroxide. What can we use that to calculate? All right, POH. So negative log of 8.0 times 10 to the power of minus 10. What did that give y'all? What is it? Is it 1.99? What? All right, 9.1. All right, so that's going to be our what? That's our POH. So what is our pH? 4.9 is going to be our pH. Is this an acid or a base? This is going to be acidic. All right, so the next slide is going to give you 2 more problems, and it does have one additional twist. You guys can figure it out. Try to figure it out on your own before you just start telling people that you figured it out. All right, so let's go ahead and go over this one. So this one is different in the last one in that it doesn't tell you whether you're looking at an H plus or a hydroxide concentration here. But it assumes that you can figure that out just by looking at what you're dealing with. Over here, we're dealing with an acid. So because we're dealing with an acid, this is going to be your H plus concentration. So with this, we can calculate our pH. So what did we get for pH in this one? What is it? 3.1. So 3.1. And then what's our POH? So our POH is 10.9. Is this an acid or a base? It's an acid because our pH is less than 7. Now looking at the next one, you can see that this time we have KOH, which is a strong base. It's got the hydroxide. So what are we looking at here? Concentration of what? Well, concentration of hydroxide, and that gives us our POH. So what is our POH? What is our POH? One more time. 4.36, and we're just going to round that to 4.4. And then what is our pH? Actually, no, that was right. 4.36. And then our pH is what? 9.6 what? Sorry, I can't hear real good today. All right, acid or base? Obviously a base. So base right there, acid right there. So we did this right. All right, let's keep going. This is the last thing we're going to be doing today. So now we're going to calculate H plus using pH. So if I tell you that you have a specific pH, what is your hydrogen concentration? You need to be able to calculate that. Now the way to do that is pretty easy. However, it's not given to you on the formula sheet. So you just got to remember this. And the formula is just going to be, so to calculate H plus, I'm going to write it over here. To calculate H plus, that's going to be equal to to 10 to the power of negative pH. And then to calculate your OH minus, what's it going to be? 10 to the power of what? Negative POH. So go ahead and write those down. These two will not be given to you.
What is this for? What?
These two will not be given to you on the formula sheet.
Oh,
So the only thing you need to write down from this page are these two formulas that I just gave you. Over here, these are instructions on how to plug it into the calculator, but the way we do it is just 10 to the power of. So 10 caret negative pH or POH. So let's keep going. All right, so here we have a hydroxide concentration. I'm going to solve this first one with you, and then the next one you're going to be doing it by yourself. So we have hydroxide concentration. What can we use this to calculate? We can use this for POH. Once we have POH, what can we use that to calculate? We can use that to calculate pH. Once we have pH, what can we use that to calculate? We can use that to calculate H+. All right? So you're going to give me 4 values. I want you to give me the, so OH, we know it. So OH concentration, we already know that. So I need the H+ concentration. I need the pH and the POH. So go ahead. I'm going to give you guys, let's do 5 laps. All right, so let's go ahead and go over this one real quick. So they give us the hydroxide concentration. We can use that to calculate POH. So the formula we're going to be using for the first one. All right, y'all, come on. So our OH concentration is 5.0 times 10 to the power of minus 5. We can use that to calculate POH. So to do that, we're going to do negative log of 5 times 10 to the power of minus 5, which gave me 4.3. So POH is 4.3. And then we do 14 minus 4.3, and that gives you 9.7. And then once you have 9.7, you do 10 to the power of negative pH, so 10 to the power of negative 9.7. And you should have got 1.99 or 2.0 times 10 to the power of minus 10. If you got 1.9, that's okay, but rounded correctly, it would be 2.0. Any questions? Hands up if you got this exact answer. All right, good.
Why isn't the pH coefficient?
Because they gave us hydroxide, and hydroxide gives us POH. So that's why that one is 4.3.
Wait,
All right, and then the last thing, is this an acid or a base? This is a base. All right, let's move to the next one. All right, so do y'all want to do a worksheet or do y'all want to do a booklet? All right, let's do a booklet. Yeah. 1 sec.